Good morning, class. This is Mr. Roberts, Shasta High School. Welcome to a fresh week of Mathematics Online. Today we're going to be kind of summarizing what happened last week in terms of absolute value inequalities. That's two things, right? We've got inequalities, a statement that two things are not equal to each other, but how is something greater than, less than, etc. And an absolute value, how far something is like from the origin. So we went through a lot. So right now I've got about 4 problems that I'd like for us to do kind of as samples. And before I jump into these samples, it's just so you know, these are the ones that we're going to look at. What's the absolute value of 3x plus 2 is greater than or equal to 12. The absolute value of x minus 1 is less than 7. 9 times the absolute value of x plus 1 is less than 27. The absolute value of 1 half x plus 5 is greater than 8. And the last one there is 2 times the absolute value of 3x plus 4 plus 5 is less than 17. So in each situation, I recommend that we isolate the absolute value portion of the equation first. So we want to see the absolute value part of the equation alone. And I think it's preferable that we write it so that it's the absolute value and then this inequality and then the value. So write it in that order. If it was written in the other order, you could flip it around. Just make sure when you change it, right, this direction follows the one that's supposed to be greater than. For this example and this example, we're going to want to divide both sides of this by 9 first in order to get the absolute value alone. Then it would just behave like the other three. On this one, we're going to want to take away a 5. And once we've subtracted 5 from both sides, if this is greater than this thing, then if I take away 5, this is still larger. And if this is larger than this thing, if I divide by 2, this is still larger. So adding or subtracting 5 from both sides and dividing by 2 is not going to change the direction of this inequality. So just by a way of review from last week, when we have the absolute value of something, right, is, and the things that the is could be, it's either going to be it's less than, which would be this symbol. It's greater than, which is this symbol. It's going to be less than or equal to. And by the way, that is the word or. Or means that it is either less than or it's equal to. It's impossible for it to be both. So don't worry that someone emailed me last week and say, hey, 2 is less than or equal to 7. That's not true because although 2 is less than 7, it's not equal to it. So this word or means just one of the things has to happen. So if mom and dad say, hey, you need to wash the car or take out the trash, before you play the video games. You don't have to do both. If they said if you have to wash the car and take out the trash, then both of those tasks need to happen. So for less than or equal to, only one of them is true. Either it's less than or it's equal to. And the other one is greater than or equal to. And that's that symbol. And what some value, right? Some value. We've got some value that we're going to be looking at, and it's either less than, greater than, less than or equal to, greater than or equal to some value. So in the case that we've got less than or greater than, that's the part where we realize that we have an open boundary. So when we graph that or we're looking at a number line, the boundary will be an open circle not shaded in, indicating that those boundary points are not included. So if it's an open boundary, we do not include the boundaries. And if we've got the or equals to versions, those are closed boundaries. And the difference is there on a number line, we'd be shading in those points, and those points would be included in our solution. So on a number line, let's look at the three of them. So let's say that we've got the absolute value of some expression is less than a value. Okay, it's less than. It's less than. It's not shooting off to the left or right, but it's contained within a region. So if I would start with my two open boundaries, an open boundary there and there, for example. And because it's less than, it's going to be these things in here. So if it's less than, it's going to be an and statement. Two things have to be true. It has to be less than this boundary, and it has to be greater than this boundary. Both have to be true. I can't say or, because if I said or, it would literally be the entire number line would be a solution. But for a less than, it has to be smaller than this. And you notice these are smaller over here too. So if I'm just saying smaller than this boundary, all of these points are smaller than that boundary. has to be smaller than the boundary, and it has to be greater than this boundary, right? So the only place where both of those are true, less than the upper boundary and greater than the lower boundary, are these values that are in between here. So absolute value of an expression is less than the value. This is what we're going to be looking at for our solution. If we were to switch this and we said it's less than or equal to, the only difference here now is now our boundaries are closed. All right, so we've got closed-in boundaries, which means that those boundary points are included, and it's still the stuff in the middle, right? It's less than this upper boundary, including the upper boundary. It's greater than the lower boundary, including that lower boundary. So if it's less than, it's an and. It's the stuff in between. It's less than this and greater than that one. So this is our solution here. In the case that we flipped it, and now we're going to look at greater than, further away from the region, right? So here's our greater than symbol. Back to greater than only, or so we've got our open boundary, so these boundary points are not included. But now instead of being like less than, right? Less than like in contained in here, it's not greater than that or greater than this. It's less than, it's inside of this region. Now we're going to go the opposite way. It's greater than. So now it's not including this point, but everything larger than that point, and or not including this point, but everything smaller than that point. Now this one, it has to be an or statement, clearly, because a value is either greater than, it's either greater than, it's over here, or it's over here, right? There's no value that's going to be both, and you'll see when we solve these, it doesn't matter. The values over here will be true for this, and the values over here will be true. So it's these things shooting off to this side, not including the endpoints. And then if we just add the less than or equal to, the only change with the last one is now our boundaries are included. And it's going to be still greater than, so off above the upper boundary or below the lower boundary, less than the lower boundary. And that's interesting. Like, hear how I'm saying that? It's either greater than the upper boundary or it's less than the lower boundary, right? And this absolute value thing is going to give me a positive and a negative that pops up in here. So let's take a look at a couple examples that we have. Go back to our list of examples here. So these are the ones we're going to look at. Let's just look at this first one here, the 3x plus 2, the absolute value of that is greater than or equal to 12. So I see that it's greater than, so just me kind of thinking out loud a little bit. I know that it's greater than or equal to, so I'm going to be including the boundary points, right? And it's greater, so it's going to go this way or it's going to go this way. So I know for me to break this up, right, to write two cases, it's going to be an or statement that joins those two. And I want you to think about each of these two places, right? On this first one right here on this side, we can just write that, hey, 3x plus 2 has to be greater than or equal to positive 12. Okay, so on that side, nothing changed. It's going to be greater than that boundary. But on the other side over here, it's going to be the 3x plus 2. Now look at it, right? You can see this. It's going off to the left of that point, so it has to be less than this point. It's no longer greater than it. It has to be less than or equal to, and we switch this to the negative 12. Now, a couple things to think about. Maybe a couple different ways to think about this, right? If this was an equality and I was just looking inside, I know that this thing 3x plus 2 could either be positive 12 or the 3x plus 2 could be negative 12. So part of it is that I'm considering the fact that it's the 12, which I'm living over here, or it's the negative 12 on this side. And then because it's this absolute value thing with the inequality, I'm going to be greater than this, shooting this direction, or less than it. Now you're going to see this pattern a lot. You're going to see me write pretty much the same thing every time. Regardless of the problem, regardless of the inequality, regardless of the expression or the value, you're always going to see me copy this exactly to here, right? 3x plus 2, 3x plus 2, greater than or equal to, greater than or equal to, 12, 12. And over here, 3x plus 2, 3x plus 2 is the same. This thing switched directions because now instead of being in order to be greater than or further away from here, it has to be going off to the left. So it has to be less than that. And then this switches to a negative 12. So this stayed the same. This flipped directions, and this became the opposite. Now to solve these, at that point, it's pretty straightforward, right? On each side, I'm going to take away 2 for both of these equations. So I could write this as 3x is less than or equal to negative 14 if I take away the 2. Therefore, x is less than or equal to negative 14 thirds. Or it's the case, or 3x is greater than or equal to 10. And if I divide both sides by 3, x is greater than or equal to 10 over 3. All right, so that's our solution here, right? It's an or statement that joins them. Whenever we have an or statement, I can't combine it into one super statement. So I'm just going to say, hey, it is the case that x's are less than or equal to negative 14 thirds, right? So if I could put numbers on this now, this is negative 14 thirds, and this is a number positive 10 thirds. So I'm looking at values that are less than, smaller than the negative 14 thirds, or greater than 10 thirds. So there's our first example. Nice. Let's move on and look at our second example. This one's got 9 times the absolute value of x plus 1 is less than or equal to 27. So again, our goal is to always get something so that it looks like the absolute value of the absolute value is blank, 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 or blank a value. So we want to get the absolute value alone, preferably on the left-hand side, and then it's going to be less than, greater than, less than or equal to, or greater than or equal to a value. So when I look at this problem that we're doing right now, what we probably need to do is divide both sides by 9 first. And when I do that, this becomes the absolute value of x plus 1 is going to be less than or equal to just the number 3. So now this is exactly the form that we like working with, right? The absolute value of something is less than or equal to 3. So we can now break this down into 2 cases. And just by way here, I'm going to do another little sketch. These are closed boundaries again. I don't know the numbers yet. We're going to figure those out. But it says that it's less than or equal to, less than. So that means it includes the boundary points, right? But then also it's constrained within that region. So we're looking at this situation where it's coming inside. It's going to be less than the upper boundary. Here's our upper boundary. It's going to be less than that, and it's going to be greater than the lower boundary, right? So this is going to be an and statement, less than the lower boundary and greater than the upper boundary. So we're going to break this up into two things here using the word and. So on each side of the and, one of them, it's just going to look exactly the same. X plus 1 less than or equal to 3. I just copied that and dropped the absolute value. All right, and that's talking about all of these. X plus 1, x plus 1 is less than or equal to 3. Okay, so that's talking about this. It's coming this way, so it's less than our upper boundary. X plus 1 is less than the upper boundary, and x plus 1 has to be greater than or equal to our lower boundary. So going this direction, all right? So the absolute value of x plus 1 has to be within 3 units, right? Within 3 units. Now, to solve each of these, we're just taking away 1 from both sides. This is going to be x is greater than or equal to negative 4, and x is going to be less than or equal to the number 2. I just subtracted 2, or the number 1, from both sides. So now I can see my boundaries, right? I can see that on the lower boundary is negative 4, and my x values are all greater than that. And on the upper side, I can see that I've got this number 2, and all my x values are the ones that are less than that upper boundary. When I do have an and statement, it is possible, I can leave my answer in this form, but it is possible to combine this into one statement, and I can write it like this. Here's negative 4, it's the smallest thing, and then I go to all of my x values. All of the x values live in here, and then the upper bound of that is 2. So when I write it like this, I'm just essentially saying, look, x is constrained by a lower bound and an upper bound. The lower boundary for x is -4, including -4, and the upper bound is 2, and it includes that value 2 as well. Okay, let's move on to our third example. Oh, this looks like we've taken a step backwards, and sometimes it's fun to do that, right? So the absolute value of x minus 1 is less than 7, less than the number 7. That means constrained by 7. So if I look at that, right, first of all, I'm going to be having an open boundary, open boundaries, and it's going to be less than. So this is the situation we're going to be looking at, and we're going to have the upper boundary when we're going to be below that, and we're going to have the lower boundary, right? Lower boundary, we're going to be above that. So less than, it's going to be an and statement, and it's the stuff that is within inside of these. I'm just not including the endpoints in this. Let's see. There we go. So we're going to break this up into two separate equations. Our first one is going to be, two inequalities. First one is going to be just x minus 1 is less than 7. And you can see I just copied it down, dropped the absolute value, less than. So it's going to be, it's going to come inside. It's constrained by an upper and lower bounds. So it's going to be an and statement that joins it. And it's going to be x minus 1. Now I have to be greater than the lower boundary, and I put a -7 here. So you can see this is the pattern. I keep doing this all the time, right? This just got copied down. The absolute value got copied down. The 7 got copied down. The x minus 1, right, got copied over. I flipped the direction because I need to be above the lower boundary, and and then this has to be the -7, right? So it's always going to be like this thing could be -7, this thing could be +7 if it was the equality. So you can see how I'm breaking it up like this. Okay, so to solve this, I'm just going to add the number 1 to both sides. So this is going to become x is less than the number 8, and over here this is going to become x is greater than the number negative. I'm adding 1 to that, so that's going to be a -6, right? Because I've got the number -7 and I've got a -1, so I'm adding a 1 on that and I'm adding a 1 to that, so I get that x is greater than -6. So on my number line, we can see that I do have open boundaries here. One is at -6, the upper boundary is at 8. The place where my values will work, they will work inside of here, right? Any value that I pick inside of here will work. These values will make this true. These will be false. True, false. So if I pick values above 8, they will fail to work. If I pick values below -6, they will fail to work. If I pick anything strictly greater than 6 but less than 8, I have solutions. And I can combine this also as one statement because this is an and that joins these two. I can write this as here's my -6, here's x, and here's the number 8. So as long as x's are greater than -6 and as long as they are less than 8, we have solutions that work. All right, next problem is very similar actually, isn't it? So let's just see if we can just do this without like overthinking it. So I've got it's going to be greater, right? So this is going to be going off above the upper boundary and below the lower boundary, greater. So if I lost my pen. I'm sorry. Come back. There we go. There's my pen. So on my number line, it's going to be greater, but not or equal to, right? I'm not including the bound point. These are open boundaries. So it's going to be greater than the upper boundary, and it's going to be less than the lower boundary, right? Because this is greater than, it's more than, right? It's moving away. It's not the stuff in the middle. It's the stuff above the upper boundary and the stuff below the lower boundary. So it's greater. Okay, so what do I do now? Let's see. I'm going to just write pen, not laser printer. I'm gonna write 1/2 x plus 5 is greater than my upper boundary, and this is an or, great or. So I'm going to write here 1/2 x plus 5 is less than the -8, right? It's got to be it's because I want it moving away. So this is it's like, why are you making that less than? Is it supposed to be greater than? No, because it's in this region, and it has to be more than 8 away from this region, right? More than 8 away from this thing that we're talking about. So it's going to be 8. It's going to be above the upper boundary, or it's going to be below the lower boundary. So that's going to kick it out so that it's further away, right? We come back to this graphic, right? When it's greater, right, without equal to, we're thinking this thing. Oops. I'd like to think that thing. We're thinking this thing, right? So because it's greater than, because the absolute value of our expression is greater than a value, it's those things that live above the upper boundary and below the lower boundary. Okay, so on each of these, I'm just going to take away 5 first. So on this side, it's going to be 1 half x is less than negative 13. Therefore, x is less than negative 26. So what did I do? I subtracted 5 from both sides of that inequality, and I doubled both sides of the inequality. On the other side, or, right, it's going to be the case that 1 half x is going to be greater than 3, right? So, therefore, x is going to be greater than the number 6. So that's my solution. Just the last line that I wrote right here. X's are less than negative 26, or they're greater than 6. And we're going to write just down here on the number line, you can see this boundary. This is positive 6 and this is negative 26. So as long as I pick values that are over here, right, those will make my original inequality true, or here, these will make the original equality true. Anything in between will make it not work. It'll be false. All right, last problem, last example we have that we're going to look at together is this one. And in order to deal with this, we're going to isolate the absolute value first, right? I want to get this to a point where I'm saying the absolute value of some expression is less than or equal to, greater than or equal to a value. In this case, it's going to be less than strictly, right? So we're going to be looking at contained within, so it's going to be an or. This is going to be the points that are less than my upper boundary, and greater than my lower boundary. So that's what we're going to be looking for. So I need to first of all isolate my absolute value portion of the inequality, and I'm going to do that by subtracting 2 from both sides. So, or 5 rather. I'm going to subtract this 5 from both. Oops, go back. I'm going to subtract 5 from both sides. So if I subtract 5 from this side, it's just become 2 times the absolute value of 3x plus 4 is less than the number 12, right? What did I do? I took away 5 from both sides, right? I took away 5 from this side, I took away 5 from this side, and you can see what I got. And then I'm going to just divide both sides by 2. So this becomes the absolute value of 3x plus 4 is less than the number 6. So our whole thing is we want to get the absolute value alone first, and now this becomes a problem that we've been dealing with all day, right? Now that we've isolated the absolute value, we can proceed from here. So this is a less than, right? So it's going to be it's contained within it, so it's going to be an and statement that joins this, and we're going to have a 3x plus 4 is less than 6. And on the other end, we're going to do a 3x plus 4 is going to be greater than negative 6. Solving this, I'm going to just take away 4 from both sides, so this can become 3x is greater than, this would be negative 10, I believe. I took away 4 from both sides. Therefore, x is greater than negative 10 thirds. And over here, this is going to be 3x is less than 2. I took away 4 from both sides, subtract 4 from 4, subtract 4 from 6. And now I'm going to divide both sides by 3. So x is less than 2 thirds. And it is an and statement. And we can write this as our final answer if we want. Or we can combine this. The smallest thing that we're looking at is 10 thirds. And then we get into the land of the x's. And as long as x's don't get bigger than 2/3, those values work. So everything in between -10/3 and 2/3, and I said in between, so that doesn't include the endpoints, would be a solution for this. All right, that's it. That's our presentation today. I'm going to be doing something similar live with the class at 10 o'clock so that students can slow down and ask me questions, but I thought I should record one of these and just post this so that you can look at it and maybe a couple times on your own at your leisure. But we are doing a live session at 10 as well. So this is Mr. Roberts. Hope you have a great day, and I look forward to seeing you again soon.